Welcome to the lesson on the areas of similar triangles. At the end of this lesson, you will be able to prove that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. You will also be able to prove that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. You will also be able to prove the Pythagoras theorem and its converse. In this lesson, we'll discuss three important theorems that are based on the areas of similar triangles. But first, let's review the basics of similar triangle. Consider this scenario. It is mid-morning and Stan and Anita are waiting for their friends in the park. They're both standing beside a lamppost. Stan is getting bored, so he begins quizzing Anita. If the length of Anita's shadow and the length of the shadow of the lamppost are known, can the actual length of the lamppost be calculated? Anita's shadow measures 10 feet, while her actual height is only 5 feet. The shadow of the lamppost is 30 feet. Let's assume that the height of the lamppost is x. If you observe the positions of the lamppost and Anita, they are both standing vertical to the ground. Both form a right angle with the ground, in other words, are perpendicular to the ground. The rays of the sun passing through the lamppost and Anita make a common angle and also define the lengths of their shadows. As you can see, two triangles are formed. Now, are these triangles similar? In the two triangles, we have two pairs of corresponding angles equal. Hence, by the AA criterion of similarity, the triangles are similar. Recall that the sides of similar triangles are proportional. Taking the ratio of the sides, we get the equation 5 divided by 10 is equal to x divided by 30. On simplifying, we get x is equal to 5 multiplied by 30, the whole divided by 10, which is equal to 15. Therefore, the length of the lamppost is equal to 15 feet. Remember, when two triangles are similar, their corresponding angles are equal and their corresponding sides are proportional. But what about their areas? Will the areas be equal? Or will they be proportional? To answer these questions, let's discuss the first theorem. The first theorem states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Consider triangle ABC and triangle PQR. It is given that these two triangles are similar. We will prove that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratios of their corresponding sides AB, PQ, BC, QR, and CARP. To begin with, let's draw altitudes AM and PN on sides BC and QR respectively. Consider triangle ABC. Its area is equal to half the product of the base BC and the altitude AM. Similarly, the area of triangle PQR is equal to half the product of the base QR and the altitude PN. Now, let's take the ratios of the areas of the two triangles. On further simplification, the equation obtained is as shown here. Let's assign this as equation 1. This implies the ratio of the areas of triangle ABC and PQR is equal to the product of BC divided by QR and AM divided by PN. Now, let's consider the triangle ABM and triangle PQN. Angle B is equal to angle Q, as they are corresponding angles of similar triangles ABC and PQR. Angle AMB is equal to angle PNQ, as both angles measure 90 degrees. Thus, by the AA criterion, triangle AMB is similar to triangle PNQ. This also means that sides AM and PN are in the same ratio as sides AB and PQ. Let's assign this as equation 2. We know that triangle ABC and triangle PQR are similar. Therefore, we can say that their corresponding sides are in the same ratio. Let's assign this as equation 3. Now, recall equation 1. By applying equation 3, we can replace BC upon QR with AB upon PQ. Similarly, applying equation 2, we can also replace AM upon PN with AB upon PQ. Thus, we have proved that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratio of sides AB and PQ. Please note, side AB and side PQ are corresponding sides of the similar triangles ABC and PQR. We can similarly prove for the other pair of corresponding sides BC, QR, and CA, RP. Hence, we have proved the theorem, which states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Now, let's look at another important theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Consider a right triangle ABC. It is given that angle B is the right angle and BD is perpendicular to the hypotenuse AC. Here, we will prove that triangle ABC, triangle ADB, and triangle BDC are similar. In triangles ADB and ABC, angle A is common. Similarly, angle ADB is equal to angle ABC as both are 90 degrees. Therefore, by the AA criterion of similarity, triangles ADB and ABC are similar. Let's assign this as observation 1. Similarly, we can prove that triangle BDC is similar to triangle ABC. Let's assign this as observation 2. From observations 1 and 2, we can conclude that triangle ADB is similar to triangle BDC. This also implies that the two triangles ADB and BDC are similar to triangle ABC. Thus, we've proved the theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Next, we'll apply this theorem to prove another theorem, the Pythagoras theorem. Let's recall the Pythagoras theorem. It states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Triangle PQR with the angle PQR equal to 90 degrees is given. We need to prove that the square of the hypotenuse PR is equal to the sum of the squares of the other two sides PQ and QR. Now, let's draw a perpendicular from the vertex Q to PR. Name it QS. The perpendicular QS divides the side PR into PS and SR. We now have two triangles, RSQ and PSQ. Consider the triangles PQR and PSQ. Here we can see that the angle P is common to both triangles. Thus, angle QPR is equal to angle SPQ, Similarly, angle PQR is equal to angle PSQ, as both the angles are equal to 90 degrees. By the AA criterion of similarity, we know that if two angles of one triangle are equal to two angles of another triangle, then the two triangles are similar. Hence, the triangle PQR is similar to triangle PSQ. Since the two triangles are similar, corresponding sides are proportional. Hence, side PQ divided by PS is equal to side PR divided by PQ. By simplification, we get PQ square is equal to PR multiplied by PS. Let's assign this as 1. Now, looking at triangles PQR and QSR, we can see that angle QRP is equal to angle QRS. Also, angle PQR and angle QSR are equal to 90 degrees. Again, by the AA similarity criterion, we know that triangle PQR is similar to triangle QSR. So we know that the corresponding sides are proportional. On simplification, we get QR square is equal to PR multiplied by SR. Let's assign this as observation 2. Now, adding the equations 1 and 2, we get PQ square plus QR square is equal to the product of PR and PS plus the product of PR and SR. From the figure, we get PS plus SR is equal to PR. Hence, we get PR square is equal to PQ square plus QR square. In other words, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Thus, the Pythagoras theorem is proved. Now, let's prove the converse of the Pythagoras theorem. The theorem states that if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. We have a triangle ABC in which AC square is equal to AB square plus BC square. We need to prove that angle B is equal to 90 degrees. Let's construct a right triangle PQR with a right angle at Q such that PQ is equal to AB and QR is equal to BC. By the Pythagoras theorem, in triangle PQR, PR square is equal to PQ square plus QR square. This is because angle Q is equal to 90 degrees. By construction, we know that the corresponding sides of triangles ABC and PQR are equal. Thus, PR square is also equal to AB square plus BC square. Let's assign this as observation 1. We know that AC square is equal to AB square plus BC square. Let's assign this as observation 2. From observations 1 and 2, we get AC is equal to PR. Let's assign this as observation 3. Now, in triangle ABC and PQR, AB is equal to PQ and BC is equal to QR by construction, and AC is equal to PR from observation 3. Therefore, by the SSS criterion for congruence, triangle ABC is congruent to PQR. Angle B is equal to angle Q by the corresponding parts of congruent triangles, and the angles Q and B are equal to 90 degrees by construction. Thus, the theorem is proved. You have reached the end of this section. Before moving to the next section, let's review the key points covered. The ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. The Pythagoras theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The converse of the Pythagoras theorem states that in a triangle, if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. Hope you enjoyed this learning experience.